This is the introduction to Docker that I wish I had when starting out. Most explanations I found try to open with, "It's like a virtual machine, but not as heavyweight," which I found confusing and unhelpful. I'm going to try to come at it a little differently with a bit of a longer route. And just as a warning, this is going to be mostly conceptual so that you understand what's happening when you're using Docker, so that you have a good mental model of what's going on. We won't go very far in talking about the details of how to actually use Docker. So let's start with your one takeaway. If you forget everything else, remember this. A container is a special way to run a Linux process. Docker is a tool for managing containers. So a couple things right off the bat. Firstly, this is about Linux. If you're running Docker, then you're running Linux somewhere. It might be hidden in something like Docker Desktop, or run in the background like Windows Subsystem for Linux, but you're definitely running Linux. Second, this is about running plain old processes in Linux. It has almost nothing to do with virtual machines. In fact, I'm going to try to avoid using the V word from here on out. Now, I'm going to assume that you have some experience with Linux, and that you have at least a vague notion of what I mean by a Linux process. But your experience doesn't have to be terribly deep to understand what's going on. Okay, so let's dive into the, quote, special way to run a Linux process. To do that, we're going to go deep into the mists of time to look at an ancient Unix command called chroot. This was, and still is, a very simple command that makes a process think that some other part of the file system is the root. For example, say you run a process with chroot set to /temp some path. If that process tries to access /myfile.txt, it's actually going to access /temp some path myfile.txt. But the process won't know that's what's happening. As far as it knows, / is still the root, and it has no idea that it's been chrooted. So that's one example of what I mean by a special way to run a Linux process. We're effectively exerting some control over what that process thinks is happening, without the process being the wiser. And we're doing it in a cheap and simple way by just doing some name mappings. Before we move on from this example, let's dive a little into possible reasons for using this chroot command, because, as it turns out, those reasons also carry over into Docker. Perhaps the most obvious reason for using chroot is security. If you run a process that thinks some part of your file system is the root, then the rest of your file system is safe from that process. There's no way for that process to break out of its root and somehow get at your other files. There is, in fact, a name for this setup. It's called a chroot jail. So that's one reason to use chroot. Another, more subtle reason is that it allows you to set up an environment around the process you want to run. Say that the process expects to find certain files in specific locations, but you'd rather not mess up your file system by putting those files where the process expects them to be. Instead, you could put the files in some directory of your file system that you'll treat as a sandbox. Then use chroot to make the process think the sandbox is its root. The process will access the files from where it thinks they should be, but you've kept all those files contained to some corner of your file system. Well, as it turns out, it's almost always the case that a Linux process is going to depend on files in other locations. Think about running just a simple node script. Well, to do that, you'll need a node interpreter at some specific location. And that interpreter is going to expect to load shared libraries from other locations, and so on. Normally, if you wanted to run that node script, but you didn't want to install Node and all of its dependencies, you'd be out of luck. But if you're using chroot to keep everything in a sandbox, and you're clever enough to figure out what files need to go where in that sandbox, you could theoretically find a way to run that script without actually installing Node on your machine. Okay, hopefully you're still with me even though we're talking about some Unix command that's over 40 years old. And we're going to talk about it a little more. Trust me, it will all make sense in a bit. So let's go back to that very last thing. We want to run a node script in a chrooted sandbox, but to do that, we need to make sure all the right files have been put into all the right places in that sandbox. Well, that sounds pretty daunting. We're basically talking about installing Node and all of its dependencies, but doing that all in that sandbox. But wait, what if we could run the Node installer itself in the chroot sandbox? Wouldn't that end up installing Node into the right places in the sandbox? Yes, it would. Now, usually we don't use a Node installer like that. We instead rely on a package manager like apt. So if we could just copy the apt-get command into our sandbox, we should be able to use it to install Node. Well, not quite. It turns out apt-get, like nearly any other program, has lots of dependencies that would also need to be copied into our sandbox. In fact, we'd probably need a large portion of a Linux distribution to be copied into our sandbox to get this to work. It's a bit of a chicken and egg problem. So what can we do? Well, let's think about that last bit for a moment, that part about copying an entire Linux distribution into our sandbox. Now, if you've had the pleasure of installing Linux on a blank hard drive, you might remember that once the installation process is done, you're left with a disk that has a bunch of files on it. Stuff in /user, /var, /etc, whatever. Those files are basically everything needed to get started using the operating system. It has enough stuff to run a package manager, which will let you install more things and eventually get all the stuff on your system that you want. So it sounds like we just need all that stuff that's been put on a disk after we install a fresh Linux distribution. So what if we go ahead and do that? Install Linux onto some machine, and then just make a big zip file of the entire hard drive once we're finished. Then, we copy that big zip file onto our original machine and unzip it into our sandbox. So now we basically have a whole Linux distribution, quote, installed into our sandbox directory. Now, let's fire up our chrooted process, pointing it again at our sandbox. That process is going to come up, and it's going to think that it's running in a newly installed Linux system because as far as it's concerned, that's what its file system looks like. So now we can use apt-get to install Node, and it's going to act as if it were run on a new Linux system. The package manager will correctly download all the required packages, copy all the right files into all the right places, and end up with Node installed on the machine. Of course, in reality, all of this just happened within our sandbox directory. But as far as the chrooted process is concerned, it just installed Node, and now it's ready to run our Node script. So it's a little bit like black magic. We can effectively have as many separate Linux distributions as we want on our machine, as long as we keep them in separate sandbox directories. And each one could have different versions of Node installed, or Python, or Ruby, or any other combination of software. We could even have different Linux distributions, maybe Ubuntu in one directory and Red Hat in another. And with all those sandboxes in place, we can run as many processes as we want in each sandbox, as long as each process is chrooted to the appropriate directory. All this flexibility is available to us, basically with no cost in performance, thanks to the humble chroot command, which has been around forever. Okay, enough about chroot for now. I wouldn't say our chroot expedition was 100% theoretical, but it is pretty rare to see it used this way in real life. But as you've probably guessed by now, the concepts we just explored are a close parallel to what happens with Docker containers. Hopefully it's got you thinking about how entire Linux environments can be isolated from each other without needing heavy mechanisms or big performance costs. So let's talk more about isolation. we just explored how we could run multiple processes on the same machine, but isolate their file systems from each other. And in doing so, we unlocked a whole bunch of flexibility and interesting use cases. Well, as it turns out, file system isolation is one of several forms of isolation that Linux offers. These isolations are called namespaces in Linux. And similar to chroot, they're cheap mechanisms that map what a process sees to what's actually on the real machine. But before we dive into those, let's refine our mental model of what happens in a Linux process to help us understand why these are cheap mechanisms. When a program is running, there's some portion of it that's all internal to the program. Maybe it's doing some pure math computations, or it's indexing some set of in-memory data. But at some point, most programs will need to do something external. They'll need to access the file system, or the network, or even just print some output to a console. We often think of a program as carrying out these operations directly, but in reality, that's not exactly what's happening. Linux, like most operating systems, is built around a software component called a kernel. The kernel has complete control over all of the system's resources: disk, network, hardware interfaces, etc. The kernel is the only component that can access these resources. Any other program in the system that wants to use these resources must go through the kernel using system calls. Now, the kernel is also the only component that can start other programs running. And the kernel keeps track of those programs with internal structures that we often call processes. These structures store information about the running program, like its process ID, which user is running it, its current directory, etc. So whenever a program makes a system call, the Linux kernel can use those structures to figure out, first of all, which process is making that call. And then it can respond appropriately. It can enforce permissions, for example, or perform file operations relative to the process's current directory. And this is also where the kernel can start taking some liberties with a process. In the case of chroot, for example, the kernel's process structure stores what root should appear for the process. It interprets all of the process's system calls against that alternate root directory. So, using a simple and cheap mechanism, we have a way to isolate processes from each other at the file system level. This is the approach that is generalized into the concept of Linux namespaces. They're simple mapping mechanisms stored on the process structures, and they have the effect of isolating process resources from each other. Now, over time, several kinds of namespaces have come into use. Some of them are a little obscure, but a few are worth calling out. The file system isolation that we've already explored is handled by mount, or MNT, namespaces. That lets the kernel control what a process thinks is mounted into its file system. Next is the PID namespace, which is used to isolate knowledge of other running processes. You're probably aware that you can list out all of the processes running on a Linux machine, and that each process has a number, which is its process ID. Well, let's say that you want to run a process in an isolated way so that it doesn't know about the other processes running on the machine. That's when you'd use a PID namespace. A process running in this way can still try to list out the running processes, but all it will see is its own process, plus any other processes that it spawned. On top of that, the process numbers that it sees will look like they were started on a fresh system. That means the process will think that its process number is 1, even though it's actually something else on the real machine. And the next process it spawns will appear to be process 2, etc. In other words, it will appear to the process as if it's the first process running on a fresh new machine, and is spawning more processes into that environment. It will have no idea that there are other processes running outside of its isolation, or even know that it's isolated at all. But similar to our file system example, those processes aren't isolated from the real machine. If you list all the machine's processes, you'll still see the ones running in those isolated namespaces. But you'll see them with their real process IDs, rather than the ones visible within the namespaces. The last namespace we'll talk about here is the network, or NET, namespace. We won't go into too much detail, but probably the most widely used feature of network namespaces is the ability to map server ports. An isolated process can, for example, start listening on port 80, but its network namespace can map that to port 3080 on the real machine. Just like the other namespaces, this is accomplished by simple and cheap mappings. There are no simulated network appliances or anything like that involved. Okay, so to summarize, Linux offers some cheap ways to isolate processes from each other, isolating file systems, network, processes, etc. When you add all these isolation mechanisms together, you end up with a system where you can control nearly the entire environment around a running process, to the point where that process doesn't even know that it's been isolated. As far as it can tell, it thinks it's running on a machine all by itself. And by controlling the contents of the file system seen by that process, you can effectively present that process with everything it needs to run, including a full Linux distribution, package manager, and other installed software. So, to recap, we can create namespaces in Linux, and we can run processes in those namespaces, isolating them from each other. And hopefully by now you're convinced that the isolation mechanisms, these namespaces, come at very little cost because they're just simple mappings. Now we're ready to start talking about Docker. Docker is a way to organize and manage all of this. We talked at the beginning about containers being a special way to run Linux processes. Well, now we know that a container is just a concept built on these Linux namespaces and the isolation that they offer. Docker, meanwhile, is a system for making all this manageable in a user-friendly way. Docker takes care of all this namespace business so that you don't even need to know that namespaces exist. And in fact, you could probably go through the rest of your career never hearing about namespaces again. Anyway, all this is boiled down and hidden behind some simple commands that you can run from the command line. So now let's talk about Docker images. The most basic requirement to start a running container is some sort of pre-populated root file system. And that's the easy way to think of a Docker image. It's basically a snapshot of that file system, ready to turn into a live file system when a container is started. Now, earlier, back when we were spending way too much time talking about chroot, we talked about taking a snapshot of an installed Linux system and turning it into a zip file. And that's not a bad analogy for a Docker image, except that the image isn't actually a zip file, it's some internal format used by Docker. But it's a similar idea. But there's another important difference from the zip file analogy. Back when we were using the zip file to create a file system, we had to unzip that file somewhere before we could start running a process. And while that works, it's also very inefficient to have to unzip a whole file system every time we wanted to start a container. So that's not what Docker does. Instead, when a container starts, Docker uses the image directly, treating it as a read-only file system. That way, no copying or unzipping is needed, so a container can start up very quickly. And because the image is read-only, it can safely be shared among multiple containers simultaneously. Of course, a container is probably going to need to write to the file system, so a purely read-only file system isn't going to cut it. Docker addresses this by setting up a place for file modifications to go, while leaving the original image intact. If the process wants to read from a file, Docker will first check those file modifications to see if the desired file has been modified. If it hasn't, then Docker will drop through to the read-only image. You'll sometimes hear this arrangement referred to as a union file system or overlay file system. And it's a good way to get the best of both worlds. the efficiency of a read-only file system with the functionality of a read-write file system. So the file system effectively contains two layers. The bottom layer holds a read-only set of files, and the write layer on top holds any modifications. Now, what if you want to add to the image? Maybe your process has made some modifications, and you want to be able to pass those modifications along to your coworker. Well, we can't modify the original image file. It's read-only after all. But what we can do is freeze our file modifications into a new read-only layer and treat the two layers together as a new image. And when we start a new container on those two layers, Docker will again add a new layer on top to hold any new file modifications. And of course, all of this is invisible to the container. Docker takes care of merging all of those layers together so that it appears to be a single read-write file system. Now that we have two read-only layers and one write layer on top, what's to stop us from freezing that top layer and having 3 read-only layers? Why not 100 layers? Well, why not indeed? A lot of work has gone into making these layer cakes very efficient. They're pretty much the heart and soul of Docker. And as we'll see in a second, this building up of layers is something you'll be doing a lot, using a clever mechanism that Docker provides. But right now, let's look at this using actual Docker concepts. Docker really does have a concept of layers, which Docker stores in some internal format. Docker also generates an ID for each layer. That ID is sometimes called the digest, because it's based on a hash code that uniquely identifies the contents of a layer. You don't need to know much about these digests, but you'll be seeing them a lot when you download or build these layers. So a Docker image is actually a stack of layers, or more accurately, a list of layer IDs. When Docker is going to use an image, it takes care of finding the data for those layer IDs and assembling them into a read-only file system stack. Now, we saw how this layering concept lets us start containers quickly by mixing read-only and read-write layers. But it turns out there's another big advantage to using this layering concept. There are many cases where multiple containers and images will share layers, which means that the shared layers only have to be downloaded once for all of those images. For example, let's say we're putting together a Docker image that has Node and Python and our application installed on it. Typically, we would start with a base Docker image of something like Ubuntu 22.04. That's a full distribution of Linux. Then we'd install Node and create a layer from that. Same with installing Python. And finally, we'd install our application and then create a Docker image that points to all 4 of those layers. Now say that we need to build a different Docker image, this time with Ubuntu 22.04 again, but with Java installed and our Java app. Well, again, we would go through the same process, starting with Ubuntu 22.04 as our base, installing Java, creating a layer, then installing our app, creating a layer, and finally creating a Docker image referencing those 3 layers. Now, because we've broken our image up into layers this way, we can take advantage of the fact that both images share the same bottom layer. So if, for example, a machine needed to have both images, it would only need to download the bottom layer once and cache it for use by both images. This is an important design consideration when building multiple images, or even during development when you're building multiple versions of the same image. You typically want to get the stuff that's least likely to change into your image first, then put the more volatile stuff at the end. That way you'll maximize your changes and your chances to share layers, and all the efficiencies that come with that. So now let's talk about what's involved in actually building a Docker image. Docker does provide a procedure for building up an image in a fairly clever way, tying the execution of a single command with the creation of a new layer. The build procedure is based on a script that you provide called a Docker file. In this file, you specify a set of shell commands which Docker will execute one at a time freezing the file system changes after each command into a new layer. You also need to give it a base image to start with. We'll talk about where that comes from, but for now, assume that you can just get an image of some starting point like Ubuntu 22.04. So let's say we're going to build up that Ubuntu Node Python image described earlier. We would start with that Ubuntu 22.04 base image, then specify a couple apt-get commands to install Node and Python. Let's start with that first command to install Node, apt-get install-y node.js. Now, let's think about what's about to happen here. Docker is going to start up a container to run this one command. The container will be set up with the Ubuntu 22.04 base image, so it will think that its root file system is a fresh install of Ubuntu 22.04. The container will also have a write layer on top of the base Ubuntu 22.04 layer, and any file system changes from running this command will end up there. So now we're about to run the above apt-get command in the container. But before we do, let's be clear about where this apt-get command is going to come from. It's going to come from the image used by the container. It's not going to come from somewhere on your host machine. So you don't have to have apt-get installed somewhere on your computer. You just need to have an image with apt-get on it. And the Ubuntu 22.04 image happens to have that program at user bin apt-get. Well, how is the container going to figure out that apt-get is supposed to be run from user bin apt-get? Well, the same way any other command is run. It will search the path environment variable. But what is the path variable set to? And that brings up an important bit of information about images that we haven't talked about yet. Before, we said that an image is essentially a snapshot of a file system organized into a set of layers. Well, as it turns out, an image also carries a few more tidbits of information that are used to set up a container's environment. One of those tidbits is a set of environment variables that will be available to any container started from that image. For the Ubuntu image, there's just one environment variable that's in the image, and that's the path variable. So any container started with that image is automatically going to have that environment variable set. And that's how the container will find the apt-get command at user bin apt-get. Now there's another thing to know about images, which is that they specify the user account that will be used to run commands by default. In many cases, an image will define that default user to be root. And Docker users will often choose to run everything within the container as root. This can be a little unsettling at first. And in fact, the whole notion of users can be somewhat confusing in Docker. That's a topic for a different time. But for now, just know that the container will run the above apt-get command as if it were the root user. And just as an aside, this is why you usually don't see sudo used with containers, including when running apt-get commands, which is one place you'd normally expect to see sudo. Okay, so that was a long and winding road, so let's recap. We have a container using the Ubuntu 22.04 image. We have our first apt-get command in our Docker file. The image's path environment is set up to find apt-get at user bin apt-get. And we're about to run the command as if we were root. So now the apt-get command runs and does everything it needs to do to install Node.js. It does some reading and writing from the network, reading and writing to the file system, and eventually it installs the necessary software by writing it to the write layer in the file system. And as always, the apt-get command has no idea it's running in a container. It just does everything it usually does, thinking it has a file system all to itself. Once the command completes successfully, which means it has an exit code of 0, Docker takes everything in the write layer and freezes it into a new layer. Now we effectively have a new image with 2 layers. Docker then repeats the process, moving on to the next command in the Docker file. It creates a new container, pointing at this new image, runs the next command, freezes any file system changes into a new layer, then repeats the process for each subsequent command until the end of the Docker file is reached. The end result is an image that's a snapshot of the file system after running all the commands, but separated into layers built from each command. Now, these separate layers might seem excessive at first, but they're a big win when it comes to caching and rebuilding images during development. Docker works hard to reuse layers whenever it can. For example, if you have a Docker file with 50 commands and you change the very last command, Docker will reuse the previous 49 layers and only rerun that 50th command. This makes the Docker development cycle much faster than it would be otherwise. So with that understanding of how an image is built from individual commands, let's look at the real syntax of an actual Docker file. Here's a Docker file that does what we just talked about. The from instruction says that the image should start with the Ubuntu 22.04 image. Then run 3 commands. The apt-get update command is needed in order to set up the package manager. It's often the first command you'll see executed in a Docker file. Then the next command installs Node, and the last command installs Python, and that's all there is to it. As you can imagine, there are actually quite a few more instructions that you can use in a Docker file. We'll go over a few of the important ones. The first is the env instruction, which lets you set an environment variable in the image. As we mentioned earlier, the Ubuntu 22.04 image has just the path environment variable set. But as you build up your own image, you can also add your own environment variables. And any container that runs with your image will automatically have those values in their environment. The environment variables will also be seen by subsequent instructions in the Docker file, because those instructions are being run in containers from the image that you've built to that point. Next is the user instruction, which changes the current user in the environment. Earlier we said that the Ubuntu 22.04 image leaves the current user as root. But with this instruction, you can change it to some other user who already exists in the image. Subsequent commands in the Docker file will then run as that user, and containers started with the resulting image will come up by default as that user. As we hinted at earlier, this is used less often than you'd think, since a lot of Docker work happens as root. Now, one element in the image we haven't discussed yet is the working directory. This can be set in an image, and when a container starts from that image, it will, by default, start with that as the specified working directory. In the Docker file, you can use the workdir instruction to change that working directory. The new value will be stored in the image and will also be used by subsequent commands in the image. The cmd instruction sets an initial command on the image. This is, by default, the command that will be run by a container starting with that image. You'll often see this used in single-purpose images that are meant to run a specific app, like MySQL or Apache. Finally, the copy instruction will copy files directly from the host system into the image. This is useful if, for example, you want to copy your built application into your image. Now, you can't specify any old file in the host system. Instead, when you build the image, you must specify a directory called the build context. That will be the source of these files. The copy instructions will then reference files relative to that build context directory. So those are some of the most common instructions you'll likely encounter in a Docker file. Now let's move on to the concept of naming images. All Docker images have a unique identifier, which is typically a long hash of the image's contents. You can always refer to an image by this identifier. But after you start building up a pile of images, which happens much more quickly than you'd expect, it helps to be able to reference them by readable names. Docker actually specifies a naming system for images. This system not only creates readable names, but also embeds information about how an image should be downloaded or uploaded. The name contains 3 main parts: a registry location, a path, and a tag. The registry location, specified as a host and a port, identify the server that should be used to download or upload the image. This server is called the registry, and if you don't specify one, it defaults to the Docker Hub community registry that's run by Docker. Usually you won't specify a registry when you're starting out, or if you're only working with containers locally. The second part of the name, the path, is what you'd normally think of as the real name of the image. This is typically organized like a path name using slash separators. Now, if you're using a name in a shared space like the Docker Hub registry, then there may be some uniqueness constraints or other naming constraints enforced. Finally, the tag part is used to indicate a specific version of the image. Docker doesn't specify any naming scheme for the tag, except that by default it's called latest. So you could use a commit ID or a build execution ID or a semantic version ID or any other scheme that you want. In fact, it's perfectly fine and even encouraged to use multiple names to refer to the same image. For example, you could use the tag latest and also use a tag with the commit number. Now, let's move on to talk about Docker image registries, and the public community Docker Hub registry in particular. This is one of the jewels of the Docker ecosystem. It contains images for all sorts of software made freely available to all. Now, a registry is just a server from which you can download or pull images, and possibly upload or push images for others to pull later. Images can be pulled to your local machine using the docker pull command, and pushed using the docker push command. By default, images will be pulled and pushed to the public Docker Hub registry. This will happen if the name you use for an image doesn't specify a registry hostname. If you do want to use a different registry, like an internal corporate registry, for example, then you would need to assign a name to the image that includes that hostname. Once you've done that, you can use docker push to upload to that registry. First, though, you'll probably need to do a docker login command to establish your credentials with that registry. Amazon's AWS also has support for Docker registries through its Elastic Container Registry, or ECR, service. It works the same as any other private registry, with its own registry hostname, which tends to be fairly long. It also requires a Docker login, but you need to obtain the password differently, so you'll often see it used in conjunction with AWS's get login password command. Now, going back to the public Docker Hub registry for a moment, it's very important to know that Docker Hub has a rate limit. You can only pull 100 images every 6 hours anonymously, or 200 images every 6 hours if you use a free login. And that works out to about 3.5 or 7 minutes between pulls, respectively. Now, if you're in a situation that anticipates doing a lot of Docker builds, perhaps with an automated build system, you'll need to keep this in mind. Now, when we're talking about registries, there can be some confusing terminology around image names. Earlier, we said that an image name specifies a registry, a path, and a tag. But when we're talking about pushing and pulling from registries, that middle path portion is called the repository. That's because of the way a registry is typically organized. A registry will have many repositories. Each of those is identified by a path. And each repository will have multiple versions, each identified by a tag. In the end, it's still the same names, but just be aware that sometimes you'll see different terms used. The next point of confusion is even more fun. We've said that an image name can contain a tag at the end of the name. We've also said that it's perfectly fine and even encouraged to have multiple names refer to the same image. None of these names is more privileged than another. So rather than saying that X is the name of this image, we say that this image has been tagged with the name X. Yes, we use the term tagged, and even call these names tags for the image, and we use the command docker tag to assign these names to images. But the tagging we're talking about here is different from the tag that's used at the end of the name. It's an unfortunate confusion, but just something to be aware of. Now let's talk a little bit about Docker mounts. We've said that an image provides the root file system for a container, that is, the file system that appears at /. However, when you start a container, you can have it also mount external sources into its file system. For example, you can mount a directory from your local file system and have it appear at a particular place in your container's file system. Well, that's kind of reminiscent of the chroot examples we were using before. In Docker terms, this is called a bind mount, or maybe it's pronounced bind mount, I'm not actually sure. This can be useful in many ways, but perhaps the most important is that it gives you a place to store persistent data. We've talked before about how a running container has a file system containing both read-only and writable layers. Well, it turns out the writable layers are not persistent. When the container exits, all those writes go away with it. So if you have data that you want to persist beyond the container, you'll need to make sure it appears in a mount like this. Now, one issue with mounting external directories is that it can be quite slow compared to the rest of the container's file system. This is particularly true on macOS, but Windows also suffers from this. To address this, and some other shortcomings of bind mounts, Docker provides another kind of data storage mechanism called named volumes. A named volume is basically a persistent file system that you can create very easily. For example, you can just say docker volume create my volume, and a new empty file system will be created. You can then mount that volume into a container at a location of your choosing, and any data written there will be persisted in the volume. You can even mount the same volume in multiple containers simultaneously, and they'll all be able to use that same volume. And unlike file system mounts, volumes will be running much faster. Volumes are managed entirely by Docker. They're stored in a location internal to Docker, and you're not really intended to be able to get at them directly. You can use Docker commands to list them, or destroy them, or see how big they are, but you can't just open up a volume and inspect its contents. You have to mount the volume in a container, and then run commands from within the container to manipulate the volume. Nevertheless, Docker is pushing pretty hard to get people to use named volumes instead of bind mounts. So, we've been talking a lot about Docker concepts, containers, images, layers, Docker files, registries, volumes. Let's take a moment to talk about what Docker actually is. When you install Docker on your system, what are you actually getting? Well, Docker is basically an assorted set of utilities that, for the most part, manage three things: images, containers, and volumes. The images and all their layers are stored somewhere on disk under Docker's control. Docker takes care of creating and building and downloading and uploading these images, and also handles the caching of layers that we've talked about earlier. The containers, as we've noted before, are just isolated environments based on Linux namespaces. Docker creates and destroys these containers and keeps track of the containers that it's created and the processes that it's running in those containers. The volumes, like images, are also stored somewhere on disk and are managed by Docker. Now, Docker packages all these utilities into a server that runs as a daemon process. That's what people mean when they talk about the Docker daemon. The daemon typically listens on TCP port 2375. And applications invoke Docker functions by running command line utilities, which connect to that port on the application's behalf and send requests to the daemon. By default, those utilities connect to the local host, but that can be changed by setting the Docker host environment variable. Now, you can actually get pretty far with Docker without knowing that there's a server involved. But there are times when it can become important, and we'll talk about that at some other time. So we've covered a lot here. We've talked about namespaces and containers and images and registries and the Docker daemon and more. And yes, we haven't yet covered how to actually do anything with Docker. But the goal here was to establish a good mental model of what's happening when you use Docker. Later, we'll cover more practical aspects of using Docker that will build on these concepts, or you can find your own guides and tutorials. But hopefully this foundation will give you a better understanding of what's happening as you make practical use of Docker.